I think my presentation will be relatively easier given the information provided by Kevin and
Great.
Tim, and also the introduction by Dr. Salman. In April, I gave similar presentation but for filling period. Now this one for the steady state condition after the dam is filled. What are the impacts on hydrology and water resources downstream? This is again Roseris, Senna, Marawi, and this is High Oswan Dam. That is the domain of the model. So I will show you the approach of the study and the impact on reservoir operation, that is hydropower and irrigation specifically, and the hydrology, the water level. This is a modeling team. In fact, it was a big study signed by the minister. It took like 2 years. Dr. Salman gave already this introduction, and here I wanted to emphasize about the seasonality of the hydrograph of the Blue Nile. Most of the flow comes during August, September, October. That's why you see all the dams on this part of the Eastern Nile. This is the position of the gate. See, this is a hydrograph before the gate. The blue in August, the peak. And the brown color is after the gate, assuming fair power generation, a steady kind of turbine operation. So, what will be the impact downstream? I mean, if we can imagine this is a Nile and everything will be influenced. The hydropower, irrigation, floodplains, floods, because the peak will be chopped off. Sediment, ecosystem, green industry. I will only concentrate on reservoir operation part, that's the irrigation, hydropower, and the hydrology, this part. So this, I'm not talking about. Why we are doing this study? Because the previous studies done was only preliminary attempts. That was the recommendation of the International Panel of Experts. So a kind of sophisticated river-based simulation model has to be done. That's the main reason, and that's why now there is the French companies working on that. This is our approach. Mainly it's modeling. We did two types of model, river-based simulation model to assess the impact on reservoir operation, so we can understand the impact on irrigation, hydropower, and evaporation, and then the hydrodynamic modeling using SOBIC to understand the effect on the water level, on the hydrology. So, navigation depths, pumping, flood damage, and we also use satellite images also to assess the floodplains. We spent more than half of the time preparing the data. We did a lot of validation. We prepared 100 years of data record, half of it on daily basis and all of it on daily basis. And then the less than half of the time we did on the modeling analysis. These are the stations. This is the model we calibrated at all key stations, and this is one sample at home. Here, we reached the conclusion that the model is robust to do scenario analysis. And then we did the existing condition of 2014, and the existing condition was the gate, and then we have some more scenarios if Sudan implement new irrigation development, or new irrigation development with modified hydropower generation. So we did many scenarios, but this is 24 scenarios. Scenario 1 is the current condition, this one. Scenario 2 is the current condition plus 600,000 faddans. This is like 200,000, 250,000 hectares. If you stretch the system more, scenario 3 is the current condition plus 2 million faddans. If the Sudanese think of making another K0. And up to 12 is for the existing condition, and from 13 to 24 after the gate. Let us see the results. So here the firm energy at Roseris, if we assume Roseris will generate every day 20 hours of power throughout the year. How much time it can do that? So this is the reliability. The existing case, the existing plus 600,000 per ton, the existing plus 2 million per ton. This is the reliability curve. It says that now process can generate 20 hours every day, 80% of the time throughout the year. Scenario 2, little bit less, 78,000. Scenario 3, 68,000. After the gear, it reaches up to 98,000. Reliability of generating 20 hours per day. The total energy gigawatt hour for the existing condition now is almost like 2,000 gigawatt hour from process. Scenario 2, little bit less. Scenario 3, less, like 1,700, because the water is diverted upstream process to these Kenana schemes. After the gear, the energy generation will increase up to almost like 2,300, 20% increase. In fact, we did more scenarios. If we increase the capacity of the turbine that process, how much will be the increase? And we found it can reach up to 60%. If we move to Marawi Dam, further down, 12-hour firm energy. In fact, the design of Marawi is already, it's not making use of additional regulation on the Nile. Everything is 100%. 12 hours is not too strict. If it is 20 hours, you could see these slides a bit lower. I didn't show it because I didn't have it this morning. The total energy from Marawi in gigawatt hour is more than 6,000 gigawatt hour, and with the extreme condition, it can be a little bit than 6,000. This 3 minutes. Okay, then I have to rush. This is after the game. The reliability of water supply, we took Yasir as an example. This is irrigation supply. Before the gate, after the gate, it reached almost 100%. But I must say, even here, 90% is very high reliability in irrigation system. This is the film energy at high Aswan Dam, before the gate, and after the gate, little bit reduction. The effect on evaporation is the total loss in the basin. If we have 2 billion meter cube from Gale, 1 billion less from Aswan Dam because it's a little bit lower. It's 1 billion loss from the net from the basin. The effect, this is the hydrodynamic part. The effect on floodplains, the blue line, during August it is still over. This Juruf, we call it Juruf in Sudan. After the gate, it will not spill over. So how much is the effect? We did collected Landsat images, 30 meter, very good images, from Udine up to Aswan. And then you compare at very low season in March and at very high season in September. You see, you can see the difference. I mean, it's getting very wide when it's flood, and during the recession time when it's March. So it's very, this is the same location. This is not far from here itself. Here we can estimate how much will be the reduction using the hydrodynamic model. I will come to that. This is the most difficult part. It takes also 1 minute. The calibration of the model. So we run the model, we route the hydrograph from Udine to Dongola before the gale and after the gale. And this is the water level pattern in Kamdin. Kamdin is close to halfway from here to Khartoum. What you see, very high increase during low season and drop during the flood season. And this will have impact on pumping. This is the pumping head. And here is the saving, very rough calculation, saving in pumping cost. For example, if you have a pumping head of 5, you can get a saving of like 20% in cost. Navigation, in March, the level will increase by 2 meters. In August, may reduce by like 3 meters. This is my last slide. The positive impacts of GERD for Sudan, steady state, 20% increase in hydropower generation at Buseris, 8% at Marawi, improved reliability of irrigation for future expansion. To tap the potential benefit from the GERD, Sudan needs to increase the turbine capacity and increase irrigation abstraction up to the available water. Because we saw that with this Buseris heightening, Yasir A has been satisfied with it. Dry season levels increases by 2 to 3 meters, while flood level reduced by 3 to 4 meters. That will improve navigation and pumping cost. Sediment load will decrease. We didn't do too much calculation here, in fact. While the bed load will decrease significantly, but the suspended load will decrease a few years to come, but it may go back again. The negative impacts of GERD for Sudan floodplain area after GERD would reduce to half. Unsecured operation of reservoirs, reduction of flow during clear state. Coordinated or at least informed operation of the GERD is a must for operation of Sudanese reservoir, otherwise these benefits may change into risk. Thank you very much.